important structures in molecules. So here, you're looking at the OH, the hydrogen. Let me actually unpack this a little bit. I know I've said these kinds of things before, but just to make sure it's clear, since I will ask these kinds of questions. The hydrogens here, where are they connected to? The carbon. Are those acidic hydrogens? No, they do not come off easy. So they're not acidic. They're not going to come off. That's your assumption. When you get into organic chemistry, you'll see sometimes you can take them off, you get carbocations, and they do all kinds of different things. But for the basics of whether or not it's acidic or basic, they don't come off. So the hydrogen that's coming off is coming off the oxygen. Okay, that should be pretty clear. So these are not coming off, they're connected with carbon, these are connected with carbon. Just making sure we understand the terminology here when you look at something like this. So this one here has a higher pKa than this one. This is the alcohol. This is the carboxylic acid group. Okay? So what does that mean when this has a higher pKa than this? Is this one weaker or stronger? Weaker, right? So this one's weaker because the pKa is the negative log of the Ka. Okay, the Ka is what? The amount of something that dissociates, because the Ka has the products on top concentration divided by the reactants. The higher the Ka, the more it moves in that direction. Yes. If it's an acid, that means the more it separates, the stronger the acid. Keeping all those ideas together, right? One thing you can do on anything, if you're ever not sure, plug in, and I've done this on the board, plug in what it actually is so that you can visualize it, instead of trying to think of it how I just thought it out, right? So if you're saying, is it Ka, what is a Ka? Then just kind of look at that and say, okay, the Ka here, and I'm looking at this thing, so what is it favoring when I do this over this? These are the products, these are the reactants, it's favoring the product. Yeah. Right? If you're still not sure, you could take this, you take the negative inverse log of this, the negative inverse log of this, which Ka is higher? Right? If you get confused, just plug it back into what you know and make the comparison. Okay, that's a pretty nifty trick in a lot of things beyond just chemistry, obviously. If you have something, an equation, and you're comparing two things, just plug them in and then compare. Then you could visualize what it is. Break it down to something that's more simple like this, because the pKa has that difference. So what does that mean? That means that this is a lower Ka than this, so it's the inverse. Right? And if you can't see that, then just plug them in, spend that extra couple seconds to plug them in and get those numbers. And then from something that you're more familiar with, then determine which one is more or less, and therefore stronger or weaker, and all the other associations you have to make with that particular topic. Okay, so the carboxylic acids are stronger. Why is this a stronger acid, and what does that actually mean? So here's another interesting thing. When I say stronger or weaker in terms of acidity, right? That just means that a stronger acid separates more, which means that it's not connected as tightly. Right? Once again, and I know I've emphasized these things, but I'm just kind of reminding you, because on the test, this is exactly what gets confusing. Right? Stronger or weaker, what does it mean? Make sure you understand the meaning of it. So that means this is a stronger acid. That means this is more easily coming off this complex than this one. Why?
It can be localized?
Because this comes off, this becomes negative, this comes off, it becomes negative. That means you have an increased electron density around those oxygens. But this one can be delocalized from this one by moving up through here. This one can also take some of that electron density. Whereas this one, where does it go?
No.
Right.
Nowhere. So that means it's harder to pull this one off because it's not as stable of a complex after it comes off. Right? You see that once again, I'm making a lot of associations with one thing. And that's the confusion you'll have on the test. So I'm going to ask these kinds of questions. Quite a few of them. Right? In this context. And this is what you need to know. So that's why I'm emphasizing it. Okay? Not necessarily just these compounds, but these are the things you need to know for that. Because does this make sense now? How this works? And this kind of wraps up sort of like a summary from some of the things we've already done? Okay. Okay, so what do we have here? Carbon is bound to two hydrogens, and we know that. Oh, this is just explaining what I just said. Okay, no big deal, right? Anybody need further explanation on this? Everybody see how I broke down all those different things to come to that conclusion? I didn't just start, this got to the point so that you're competent to understand this, but it doesn't just start here, right? That's why I made all those other associations so that you could break it down intellectually and understand what's happening, as opposed to just saying, oh, well, this is a completely separate thing from anything else we've done. This is exactly what we've done prior, and then we've just added things to it so that you can get to the point of making all those associations that I just made. Okay, so here you can see this is just a representation where this one, you just localize the electrons around here, there's nowhere else for it to go. And over here, this is after the hydrogen comes off. Hydrogen comes off here, and you can see that you could form two different compounds here, which really, if you recall, these are resonance structures from Chem 101, and that means that you have this delocalization of electrons where they're actually going in between. And out of 101 memory, how do you know this? How do you know that they don't exist like this, but they exist more like this? What was that? We actually talked about this. What about? let me lead you a little bit. Is the length of this double bond the same as the length of that single bond?
Oh, no.
No. Is that starting to recall a little bit? Mm-hmm. When you actually look at the lengths of these, is the length just a combination of double bonds and single bonds? Or is the length is more a mixture? So if this is, say, by the way, which one of these are shorter or longer? The double bond or single bond is longer or shorter?
No, double bond is shorter.
Double bond is shorter, right? So this is a shorter bond length.
Right.
Picometer, remember? We looked at picometer. So what we actually see in something like this with resonance structures, do we see let's say this is 2 and this is 4 in terms of length. What do we see here?
3.
More like 3.
Yeah.
That's how we know, right? Experimentally. These things are determined. So remember, that was 101. These things are determined experimentally. So we know that it exists more like this. And why? Because it's delocalizing the electrons. So that they're not all sitting on one area, making it less stable. That stabilizes the compound in the way it is without that extra hydrogen. Obviously, it's a little more stable with the hydrogen, which is why it's in there, right? Because this isn't necessarily a strong acid. It's a weak acid that's stronger than the other weak acid that I showed you, which is this thing here, the alcohol. Remember, keep that definition. Strong acid versus weak acid, and then the level of strength within the weak acids, right? And that's kind of what we're discussing. Okay. What do we have here? Okay, so now we're going to look at something else. I'm going to add something once again. Maybe a question on the exam or these kinds of things. I'm going to add now. I have, and I want you to notice this. I have 1, 2, 3, 4, and if I get rid of these things, or I get rid of each one of those, they're all the same if I just add a hydrogen here, right? So here, this is just adding the if I wanted to emphasize what was here, it's just the third hydrogen, right? I take off a hydrogen, I put a bromine. I take off a hydrogen, I put on a chlorine. I take off a hydrogen, put on a fluorine. All based on this here, based on the similarity of the carboxylic acid structure. Okay. Mm-hmm. And what I see is that I actually, once again, all weak acids have a difference in pKa's between them, which means that there's a varying degree of weak or strong, depending on how you want to look at it, within them all, right? Mm-hmm. And then the question is, what is that? Okay. So here, pK is 4.76. So this would be the strongest or the weakest of these? Weakest, because once again, the pKa is the opposite of the Ka, right, which means that you form the least amount of product relative to the others. So here, the pK, the Br is that makes this a little bit stronger. Stronger acid means that this is going to more easily come off than this. Not a whole lot, but a little bit. Right. This one will come off a little more easy than those two. This one will come off a little more easy than the others, even though these are pretty close. Mm-hmm. But there's still a difference in the pKa. Why is the question?
Ionization energy?
Okay. So if this is more electron negative than this, mm-hmm, and that's exactly right, you're looking at electron negativity. If this is more electron negative relative to what? It's connected to this carbon, which means that if this is more electron negative, are the electrons going to be pulled closer to the fluorine or closer to the carbon in this one?
Fluorine.
Closer to the fluorine, which means that the carbon-carbon interaction, what's going to happen between those electrons?
You're gonna pull.
They're going to probably come a little bit closer to this one, since this one's lacking some electron density from the fluorine. So then what happens between these? Pulls it a little bit away, creating a greater electron negativity difference.
Mm-hmm.
Even though it's 1, 2 away from the actual CO bond, it still pushes some of the electron density around the molecule so that now when this one comes off, it's a little more stable. Everybody see that? And this one is going to create a little bit more stable than this one, or less stable than this. More stable after the hydrogen,
Yes.
less stable prior to the hydrogen. Let me make sure that's clear what I'm saying. Once again, you see the reference point is really important in what I'm discussing here, right? Because you can take one thing I say and twist it the wrong way. Okay. So let's assume that the hydrogens are now off. That makes this a more stable complex than this. This is more stable than this. This is more stable than that. Hence, that's why it's easier to pull off that H. Okay, go ahead.
Can you consider it an acidic hydrogen if it's not connected to oxygen? Like, could it be connected to something else and be easily?
So let me just, I'll go back to one thing. 2 types of acids, binary and oxoacid. So this is the oxoacid version. If it's binary, it wouldn't be connected necessarily to oxygen. It'd be, say, HBr, HCl, HF. So those would be the 2 acid types that you're worried about. So can it be connected, or potentially, if you think of, I guess I should add this. If I take NH3 plus H2O, what is that, a weak base? And it will form what as a result? That's why it's a weak base, because it forms that in water. Of course, it's a weak base in water. Hence, that's the solvent of choice here. If I put it in something else, it may not do that, and therefore it wouldn't be a weak base. So I want to make that clear. I know we always talk about it in the context of water, which is really important in this class, but you don't always have everything in water. So if it's not in water, water as the solvent, then it completely different properties potentially, right? Just keep that in mind. So then if I now, what is this from here? The conjugate? Conjugate acid. So that's kind of like an acid, because now if I just take the NH4 and I put it into water, what can happen?
Then it gives us the hydronium.
Right. They can give it off, right?
Right.
And now I get the H3O plus, plus the NH3, and now there's your acid. So, but in general, we're discussing oxyacids and binary acids, not a conjugate acid, because now you already have it in water and some other dynamics are already going on to create that. Okay, so this probably, so this should explain everything. And this is called the inductive effect, by the way. Okay, so this is the term for this is inductive effect. Oh, here we go. But this is the same slide. So this is the inductive effect. Let's see, is there anything new here that I haven't already discussed? We can call this the inductive electron withdrawal. That's another way to state that. Okay. Does it really matter the term? Am I ever going to really, just on a test, ask you what the inductive effect is? Probably not. But if you see this kind of thing on a multiple choice, then you have to determine which one it is. And if the question itself uses the term inductive effect, you have a sense of what that means. Okay, that's all. Okay. Any questions on this? This okay? Hopefully this doesn't look too easy here, and then all of a sudden on the exam it gets hard, because that's what happens a lot, right? So make sure you take notes and pay attention, and then make sure in your mind you keep it all together for the exam. Because it's not like you don't necessarily understand it when I'm explaining it, but then when you try it on your own, that's where the understanding breaks down a little bit and you make a mistake, right? So it is not, I'm not suggesting that it's complicated. I'm just suggesting make sure you keep it all together. Don't get like squishy with it, because then on the test it gets squishier, right? And then who knows what, you got a 25% chance of getting the right answer. When you really already know it and it's not that challenging and you should get 100%. Okay, we're going to talk about inductive effect. Okay, so one scenario is this where it's connected to the same position, so it's easy to compare. What if I have a longer molecule, and now it's connected at different positions in that molecule, right? There's still an inductive effect, and that's going to look something like here. So what I'm going to show you here now is a much longer carbon chain here connected to the carboxylic group. Okay? And this is good that you're hearing these terms, by the way. I'm kind of emphasizing these terms a little bit because this is what you're going to see in here in OChem, right? You're going to have to know these kinds of things. But you'll have nomenclature and other things associated with it. I'm just saying it's a longer carbon chain. Where this bromine now, I'm going to use the same thing. I could use chlorine, bromine. I could mix them. Okay. And then we'll talk about that in a minute. But here I'm going to have the bromine off the carbon closest to the carboxylic group. Now it's 2 away. Now it's 3 away. Now it's 4 away. And the point being is which one has the greatest inductive effect on the molecule, or for this example, for the acid. Okay, you can see this is the weakest acid because this has the least effect of this interaction the further away it is. That should be pretty intuitive, right? So if it has the least effect, when I take off the hydrogen, it means it's the least stable. So that's why it does not want to get rid of the hydrogen, and therefore is a weaker acid. Once again, very careful in how I'm choosing these words, right? Because if I slightly change something, then I'd be saying stronger. I'm emphasizing here, which is not what you're going to look at when you do your notes, is that if I take the hydrogen off, is this complex now without that hydrogen more stable? Yeah. That's how I'm asking this question. That's not implied. When you look at this, you're going to say, well, which one's stronger or weaker? That's a bad way to think about it because it's harder to determine it that way. When I take the hydrogen off, is it more stable or not as a complex? If it's not more stable, then what does that mean? Okay. Does that make sense how I'm describing that? So it's an important way to think about it. So if I take this hydrogen off, so now there's a negative here, right. Is this complex more stable than if I take this one off compared to this one? No. This one's more stable because this has a greater inductive effect from the bromine because it's closer to helping stabilize the complex without the hydrogen on it. Right. Okay? So that makes this a stronger or weaker acid than this. This one is now a stronger acid than this because it's more stabilized without the hydrogen on it. This is why I'm emphasizing how to think about it. And I can do the same thing all the way over. This becomes stronger because you get a greater inductive effect compared to this one, and this one is compared to this one, and therefore the pKa's are lower as I go from right to left, and this is the strongest acid, to the right is the weakest acid. Okay, but once again, how am I thinking about it? I'm thinking about it in the context of if I pull off the hydrogen, is the leftover complex more or less stable? Right. If it is more stable, then it's a stronger acid. If I look at it adding the hydrogen back on. In other words, it's easier to get rid of that acid because the complex is stable after. Okay. Shown below several molar. So I like these kinds of questions. Okay. And I'm going to give you a couple of these kinds of things. I'm going to say, okay, below are several molecules that can act as a weak acid. So I'm emphasizing it here. I may not emphasize that. I could give you something that has basic or acidic components on it, and you have to identify them. And maybe give a brief explanation to why you're calling it acidic or basic, right? So here, I'm specifying that I'm only worried about acidic hydrogens. So I look over here and I say, are there any acidic hydrogens on there? And if so, which one? And if it is, why? So, and what you do on an exam is you would circle it. Right. Okay, so which, is there anything on this molecule, which you may not understand what the molecule is, but so what? Yeah. Right? That's not the question. The question isn't to identify this and then name it. Right. The question is, if I look at any molecule, can I determine if something is going to be acidic? If I put this in water, I should also emphasize that. That's not something implied in these notes. right? I know I keep mentioning that, but I could put it in ethanol. I could put it in chloroform. I could put it in anything. Then it wouldn't necessarily be an acidic acid or acidic hydrogen. So this is implied I'm putting all these in water. So if I put this in water, is there anywhere on here that hydrogen could be lost to that water, forming an acidic solution? And if so, which one?
The COOH.
You see how I circle that? By the way, I'm circling the hydrogen here. Don't circle the whole COOH.
Right.
That kind of implies you're not sure what you're circling. Does that make sense?
Yeah.
I may or may not take off, depending. I've seen things where it's kind of like a wide circle, so it kind of like, yes, this hydrogen's in the middle of that circle, but what are you actually circling there? Right?
Do the O and the H, or
Just the H, in this case, I mean, it's kind of hard to separate. The main thing is, if you just do that, the H is in the center, it's pretty obvious. That's the hydrogen you're referencing. If it becomes a little bigger, now all of a sudden these hydrogens are in there, and if you do the whole you do the whole thing with the COO, now it's kind of like, are you saying that what are you actually saying, right? Make the circle clear that you're emphasizing a particular thing. Because if it was basic, what would you be circling, by the way?
The OH. Right?
No, the OH on this.
Oh, the
Yes, what is it?
If there was an NH3.
If there was a nitrogen in there, you could be circling that because of the lone pair, even though the lone pair might not be seen. If I asked about something basic. And it could be on the same molecule, so you'd say this could make a basic, this could make an acidic, right? Okay. So in this case, this is, and then what would be the explanation here? This hydrogen can come off.
Make it more stable.
And it would be stabilized, and the electrons would be delocalized by the COO. Simple. You don't have to write a whole Nobel Prize piece. Right? This is something already known. You don't have to have full, paragraphs in some small little space and on the backside. Just a couple quick things to indicate that you understand what's happening.
Wait, so if this was basic, you would circle the nitrogen, you were saying?
You would
What would make something? What are bases?
OH. OH.
By the way, this circle is the same thing as these. These could essentially move each way, so a circle indicates that you have, one every other piece connected. That's just a circle. It just means it's double bonded all the way across. COH. And what do I have here? O, N, CH3, and let's say I put an H there. Is there an acidic hydrogen there? Are there any acidic hydrogens? Let me ask that first.
Yeah.
Yeah, which one?
OH.
Okay, no problem. That's what you do on an exam. Is there anything basic on here? That would create a potential base. What? If I had H2O, what can this do?
Oh, it's going to transfer, yeah. Connected.
Pull that off. What's left here?
Into the water, yeah.
And what's up here now?
NH4.
So if I put this in water, I could potentially have this part too. If all I did was I changed the C there.
You didn't have, initially you had a NH3.
No, initially I just had NH.
Oh. Okay.
And I didn't show you the lone pairs, but you have to know that because how many bonds does nitrogen form to it? 3. So it forms 3 bonds, 1, 2, and 1 to the hydrogen. So if I were to draw this out structurally, it would look like this. So then those 2 here can do what to water?
Right.
And so you'd circle the N in that case?
Circle the N, absolutely. This would create a basic. This would create an acidic. So then overall, I couldn't ask you which one is more basic or acidic because you wouldn't know which one plays a greater role, right? Unless I gave you the pKs of each one or whatever. Right? And then, of course, that's hard to do within the molecule itself. I'd have to do the pK of something like this and the pK of something like this. And then you would assume that one would be overwhelming the other. How would you actually determine this if you were in a laboratory?
That's the
See what you
pH.
have more of?
It's so simple. pH meter, piece of paper. Put the blue thing in, and does it change? Does it change color or not? If it changes to red, a little bit red, then it would be red, right? That's not. I didn't pre-think that. I just, as we were going over it, figured, okay, let's. These are things that you guys can actually figure out already. If you're in a lab, you could, use the tools that you know, it doesn't always have to be in the same scenario you learned it in, right? That's kind of the whole point when you're doing research, is you're figuring out things that you, in context that you're not used to. Otherwise, what would be the point of doing it? You'd already know it, right? So you're going to get scenarios, it's kind of like an exam, even though I try to minimize that at some level, but you're going to get scenarios that you might not be as familiar with. Doesn't mean you don't apply what you already know to it, right? And you may not know it right away, so then what do? You think of what you do know and how, if it can apply, how does it apply, and then solve. Same thing you do in a research lab. Okay, so this, what about this one? This one right here, right? Okay.
There's also possible this.
Now, in this case, though, what am I asking? If I said, is there anything acid or basic on this molecule, then you would also circle this one. But you would express that this could act as a base because of the lone pair on the nitrogen could pull off a hydrogen from an H2O. Okay. But because it's only asking about the acidic hydrogen here, nothing's added there. Do I care about these hydrogens here? By the way, are there any hydrogens on this thing?
Yeah.
Let me ask. These are things I don't think about, and then all of a sudden I'm like, okay, wait a second. What does each corner represent? Carbon.
Yeah.
How many bonds does carbon have to it? 4. So in this case, when I do this, let me just separate this a little bit the way they have it here. How many bonds are to this carbon?
3.
1, 2, 3. So there's actually a hydrogen there. It's just not shown.
Right.
Okay. Just so you have a sense of that, because you're going to have to know that at some point soon enough anyways.
In the lab exam.
Here, same thing. So you have hydrogens on each one of these hydrogens. Can they come off?
Yeah. Oh no.
Not unless I do something more extreme.
Right.
Right? So I could pull off anything under certain circumstances, right? All I'm saying is if I put it in water, it's not coming off.
Right.
It just doesn't fall off the way these oxyacids do. Does that make sense? But if I do something more extreme than just put it in water, I could pull it off, of course. Add some energy to it, add an enzyme that's going to pull it apart or whatever. I could do all kinds of different things. But if I'm just dumping, remember, all I'm doing is dumping this into water. Does it come off? No. Okay, so keep that in mind.
So if you ask for that drawing, the structure, if you don't put the H's, it's okay? You understand that?
Yeah, it's already implied that the H's are there, which is why they're not on these. But that's why I just decided maybe I should point that out.
Yeah.
Right?
Okay.
I sometimes forget that what's obvious to me may not always be obvious to you, and I don't always get that until I start talking. Then all of a sudden I'm like, wait, maybe they wouldn't know, maybe some would know this, depending on what your experience is in bio and other things. Okay. Anyways, does this make sense? Okay, because I'm going to ask these things. Oh, look at this one. But does it always have to be just one hydrogen or something on it?
No.
There could be multiple. It depends on what the structure is. What about this one? That one?
Yeah.
Okay. Any on there? No, there's probably one there. No, none. Okay, no. Oh, what about this one?
NH.
This one, right?
Yeah.
Yeah.
You notice how you have to specify this. In this case, this is asking about the height. This already has this bound, right? This is like the NH4.
Mm-hmm.
But if it was, and with these things, this wouldn't be there. I probably wouldn't show the lone pair, the 2 electrons, but you would assume they're there, and then that could actually form it could act as a base, not an acid, right?
Right.
I'm also circling, in this case here, I'm kind of circling this thing where the H is connected, right? But in this case, you must circle this H. You don't circle the N here, because then, what does that mean? Once again, I want you to think about what you're circling, and be careful in how you circle it.
What is the positive charge for that one? On the center?
If N has 4 bonds, what's the charge?
Okay.
NH4 plus.
Right.
One thing that you can really do in these bigger structures if you get confused, assume this is just an H and H and an H. Does any of this really matter here?
No.
In fact, a lot of times in OChem, you're going to just put R. This is going to be R group.
Functional group.
Doesn't, R group will represent this whole thing.
Right.
This would, if they're the same, this would be R1, this would be R2.
Right.
The key there is if you just substitute in your mind something more simple like H, 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 and H4. Oh, absolutely. Same thing. Same concept. That makes sense?
Yes.
So you could break that down and look at it in a different light. If you get mixed up in all of this stuff here that you also don't understand at this point, then it becomes a little more confusing. If this is just H and H and an H, that's pretty obvious. Okay, so you could think of it that way.
Thanks.
Okay, so usually they'll just call it no chem. You'll just take this off and say R1, R2, and R3.
Right.
then it's kind of like looking at NH4, but you're looking at NH with R1, R2, R3. It just simplifies. It gets rid of all the mess there that looks confusing, you know, visually.
Function of groups.
Is that okay? Okay. Okay, which acid is stronger and why? I have these two things here, right? This one and, okay, so a little bit tricky because you're looking at an S and a C here. And does that matter, or does it matter that this S has more oxygens on it around where it, so, okay.
Well, that one would be.
You know, let me just remind you of what we looked at when we looked at something like this earlier.
You can do the rest.
We had a Y group connected to an O connected to an H.
Right.
Okay, so this is the acid, hydrogen. This Y group is really just the C or the S.
Right.
Okay, keeping that in mind from the earlier terminology. I know everybody in here studied, so that should recall. Now, if you have more oxygens connected to the Y, that creates a greater amount of destabilizing the electron density if I pull that hydrogen off, making the structure after the hydrogen comes off more stable. Therefore, making it a stronger acid, easier for the hydrogen to come off. So that's why most of you pick the double here. And that's right, by the way. Just some of you may say, well, wait, there's an S and a C, and how's that different up here? The S or the C going to be more or less electron negative, and does electron negativity even play much of a role here? Yeah. And it does. It plays a role between these two things, but the S and the C are pretty close, right? They're going to be pretty close in terms of electron negativity. The C, remember electron negativity, if you take the arrow and you diagonally go from the francium up to the fluorine, that means as I go from the bottom up, it increases in electron negativity, and when I go from left to right. So C is 2 to the left of sulfur, making sulfur more electronegative, but C is 1 above S going up, meaning in that context, C is more electron negative than S. So they're overall going to come out pretty close. So there's not a big enough difference in electron negativity between the S and the C and their connected O's for that to matter. The number of O's is going to matter even more in creating a more stable complex after the H comes off. Therefore, that one's going to be the stronger acid. So this one should be the stronger acid. Just put that in context. Okay. Well, they give you an example, explanation. So probably the same thing I just said, and it is. Same kind of thing. Stabilize, that just means you've increased the electron density into different parts of the molecule, which is just a fancier way of saying what they're saying here. This is a much simpler way of saying it. I'd accept either. Knowing that destabilization is important, though, because that then in your head you could visualize what's actually happening. These are just kind of simple statements saying just memorize. This is kind of like memorize me. The way I'm describing it helps you just understand it.
So you can do resonance to either one, where the other one you can do the resonance to one.
This would be resonance here. Here you could have double resonance as a way to put it. Absolutely. Delocalizing the electron density, creating a more stable complex after the hydrogen comes off. Another example. Wow, these are just... Okay, so let's list the following compounds from the strongest acid to the weakest acid. So here, I have nothing. So the first thing when I see these things hanging off, what am I thinking of?
That's where the electrons are.
Inductive effect kind of thing?
Right.
Yeah.
Inductive just kind of means internal.
Mm-hmm.
Right, okay. So once again, I'm going to say, okay, this is the acid hydrogen. This one comes off. Which complex is the most stable? That would be the strongest acid.
Right.
That's simple. Fluorine is more electron negative than chlorine.
Mm-hmm.
So that should be stronger. However, the positioning is also relevant here.
Right.
So let's start. This was going to be what? The weakest.
Yeah.
We know that. Okay. Now,
Then
once we go
second.
strongest, weakest, so we'll put this on the edge here.
Right.
Now we're looking at this one, this one, this one. This is at the end. This is the second one over from the left. This is the second one. So this one or this one is going to be the strongest. That's more electron negative than that. That makes this the strongest.
Right.
This second, that third, and that's the weakest.
Yeah.
Okay, so everybody see how that was evaluated? And you know how many times I've seen given questions similar to this or something like this, and somebody reverses this?
Oh.
So on an exam, let's say arbitrarily, let's say this is 6 points, you get it at 6 points. You mix up a couple all over the place, you lose all 6 points. If you reverse the order, I give you half. It shows that you had some understanding, you just got it wrong. Just to kind of give you a sense of how I grade these. Go ahead.
Can you run through that again, please?
Sure. So this is the hydrogen coming off.
Yeah.
So if that hydrogen comes off, which is the most stable complex, there's an inductive effect where these things that come off create a more stable complex once the hydrogen goes, that works from the closer, more stable, outer, less stable, and then whether or not it's more or less electron negative. So this doesn't have any inductive effect, so that's going to be the weakest acid. In other words, its complex is the least stable by getting rid of the hydrogen, therefore it's the hardest to get rid of that hydrogen, making it the weakest acid. Okay, so this one goes here. Then I come over here and I say, okay, this is further away from here than this and from that, so this one is going to be the next weakest, because it's going to be, if I pull off the hydrogen from this one, it won't be as stable as this or this. Okay, so that makes that here. Then I compare, these are in the same position. This one is more electron negative, so if I pull off the hydrogen from here, this will be more stable than this one. So that makes this a stronger acid because it's more willing to give up that hydrogen because it's more stable after. So that's the strongest.
Does the position of the, say, fluorine or chlorine take precedence over whether the fluorine or chlorine is more electronegative?
Depends on the structure, so I won't give you anything that you can't make these kinds of comparisons. Okay. But I also love these kind of comparisons, right? Because I won't give you anything where it could be ambiguous. And if it is ambiguous, state it. Right? If it's a regular question and it maybe I missed something and maybe...
the first one's
yeah, maybe,
that one's a
maybe I put the fluorine here, and what if I put the chlorine there?
Yeah.
Then I would probably say because it's closer, it's going to have a greater impact.
Okay.
But what if, between chlorine and fluorine, but what if I put iodide there, which is much less electron negative than the fluorine? Well, maybe now you have an argument one way or the other. If you state what your argument is, that's perfectly fine. I'm okay with that because you would never know unless you tested it.
Yeah.
Right? So, but just indicating why you did something, and if what you say is correct, of course. Indicating something that doesn't make any sense, obviously, is still wrong. But if you say something that is correct, and that's your opinion, that you would anticipate that if I had an iodide here, that this iodide would create a more stable complex than the fluorine at 1 carbon over, because it's closer, it will have a greater effect based on proximity to the acid hydrogen. That would override that it's less, even though it's less electron negative. That's a perfectly valid argument.
Yeah.
Really?
That'd be fine. Or if you did the inverse of that even.
Okay.
If you said, well, the fluorine is more electron negative,
Right.
even though it's further away, it's so much more electron negative than the iodide, it's likely it may play a greater role in creating a more stable complex after the hydrogen. Either way would be perfectly fine. Of course, if you start saying, things that don't make sense, and once again, I always preface it because I get a combination, right? Some will maybe do something like that. That's great. I actually rather leave it ambiguous and let you describe it however you want, because that's exactly what happens in a research lab, right? You don't really know the answer, so you got to make some decisions, right? And then from those things, then you'll test them if you can, but you may not have the equipment to attest it even, so you don't know. But then some people will then just arbitrarily write anything. That makes no sense, of course. I want to discourage that. If you don't know, don't write just random things. Right. Okay. Is that okay?
Yeah.
Yeah.
Okay. Now, okay, here. So now it's identify the acid. Once again, I love this because that's exactly the reaction that you would expect when you see something that you're not familiar with. And the first thing you do is, you almost get in a car accident, your heart beats real fast, right? But then you're okay after, once you settle down. You see this, your heart beats real fast, then settle it down on the exam and say, okay, wait a second, this is not that big of a deal. This is not that scary, what do I know?
All the OH.
And it's asking for the acid hydrogen. Which ones, how many? By the way, if it says identify the acid hydrogen in the compound, or the acidic hydrogen, maybe in parentheses S, that means there could be more than one.
Right.
One of the things I found in, say, 65 level is when I say those things, it's automatically chosen by 99% of students as just one thing, even though they're obviously more than one thing.
Right.
So if there's more than one, if there's only one, then put only one. There doesn't have to be 1, 2, 3, 4, whatever it is in that molecule. So don't be intimidated to write down things, but also don't write more. Like if I gave you 3, not all 3 have to have exactly 3. 1 may have 1, 2 may have 4, 3 may have 1. It's whatever each molecule is. Don't like add or take away from what it actually is. So in this case, how many do I have? I
Three.
asked.
Three.
Where are they? On this side? Anything?
Yeah, right on the bottom.
Right there?
Then in between there, and then the last.
Cool, okay. Now,
Now, or strength.
decrease in, so rank in decrease in order of strength. So we want which one, and then provide rationale. I like the, once again, provide rationale. Do not write a Nobel Prize piece.
Okay.
I already know the rationale. So nothing you put is going to be overwhelming and I'm going to, submit it as a publication or anything, right? Make it simple, but just make it relevant,
Okay.
right? So
That's it.
this one, or this one would be the strongest.
Strongest is the
Here,
last one. Yeah.
why?
Resonance.
Resonance, good enough. You could write resonance, I'd be satisfied. What else can you say?
There's an oxygen.
Delocalization of electrons. There's an extra oxygen. All that implies the same thing. You see that?
Yeah.
Very simple. You didn't have to even write a full sentence for this. Doesn't mean that sometimes when I ask for a particular sentence or whatever, I write a sentence, but in this case, it's just saying provide rationale. What I actually did on your exam this time, which I'm starting to change as I start to realize where things are, mistakes are made. I think instead of just putting, I think I actually emphasize there could be any number of acids, hydrogens on here. So however many there are on each one. I also will put something like circle them. So you'd circle this, and then the rationale here, delocalize.
Yeah.
Very simple, nothing more than that. Okay, so that's this one, this one, this one. So this is the strongest. Now between these two, which one is stronger?
I'd say the middle.
This one, and why?
You have the two H.
Because this has a variety of things connected to it where the electrons could be moved around, right? So the electron can come in here,
Right.
shift this, this, and this, and then they could keep shifting or rotating, creating a more delocalization of the electrons, where this can't really, it's just kind of stuck here, right?
Right.
Could it not like travel out on the oxygen?
Well, you mean this one?
The oxygen, the first one.
This one? This one?
Yeah, that one.
This one's the strongest. There's no debate about
But
that.
the middle one, could it not dissociate
Oh, towards the right?
electrons over to that oxygen at the very top? Like through the
Oh, through
carbons?
here?
Yeah,
It might do something, but it's got a long ways to go, though.
because that's 4 carbons there and it's.
Right. Well,
there's
here's
1,
just
2, 3, 4, 5, 6 carbons
connected.
over there.
The carbon it's connected to can distribute both sides,
Right.
because this will just move.
Or is that only H only has one? Right.
Each one of these H's have only one, so I move
Yeah.
this over, this moves, this moves.
But
The
actually
electrons
what's-
within here can move into this circle. The electrons here kind of get, where do they go?
Mhm.
Okay.
There's nowhere for, I mean, it can go here and create sort of a partial negative on the carbon, of course. But here, it can go in and it can shift the electrons around, keeping it a little more stable, even though nowhere near forming resonance structures like this. And this oxygen has a greater capacity to absorb some electron density than the carbons do. But you still have some movement of the carbons to help delocalize a little bit from here that you don't have associated with this one.
Okay.
Right? So this would be 1, there's 2, there's 3. And once again, I'm not going to ask you anything you don't know. So rationale, you get delocalization, resonance structures. Here you have lighter or movement. You could move the electrons a little bit. You could also say delocalize there. And here it's rigid. That's it. I don't need to hear any more than that. What I will get to is some won't know any terms and they'll just leave it. So 6-point problem, 2, 4, 6, you get this right, you get 3. Then you just put, say, 1, 2, 3 and identify that. Maybe you get 4, you write your explanations and they're right, you get 6. You write wrong explanations, I'll take off maybe 2. If you don't write any explanations and maybe don't even order them, then you get 3 out of the 6. That's sort of how I grade. You miss one or whatever, then you lose the automatic 2 from that 1. That's kind of how I mix and match and determine. Then based on, as I go through, what I see the differences between them, getting them all right versus getting part or whatever, then I maybe go back and make a couple minor changes to that, 1, 2 point here for somebody, or minus 1, 2 point relative to somebody else, because it is relative to each other. So just to give you a sense of how I evaluate these, right? That way you have you do know I look at these. If you notice, you'll see -2. That's why it's -2. It's -2 relative to somebody else who got, perfect, or somebody else got -4 or -3, and there's a reason why one got -3 versus one got -2. However, sometimes when I do make these changes, I then want to go back, and sometimes I may miss one. So you could always come back and say, why did I get 2? And I can always explain. Right? Okay. Summaries. Wow, this is taking a lot longer than I thought. Summaries. Electron. So if you're looking at different factors, you're looking at electron negativity increases going this way, acidity increases along with it, size increases going down, acidity increases going down. The size refers to the strength, right?
Okay,
The further away, the less strong, the closer, the stronger.
Yeah, kilometers.
That's the size, right? So if I have something like, let's say, fluoride with the hydrogen connected and chloride with the hydrogen connected, it's a longer connection, right? So that makes it weaker, easier to come off.
Right.
Talking about atomic radius or bond?
Radius or size. I mean, when I say size, I'm referring to, you could look at radius, diameter, however you want to reference it. So as the size increases, the acidity increases because it's easier to pull it off because it's further away. Okay. And then electron negativity, right? The greater the electron negativity, the easier it is to pull off because you already have the partial positive and negative per side. In other words, you already have your dipole moment. The greater the dipole moment, the greater the separation in charge, the easier to pull it off. Okay. When they're connected directly, of course, as opposed to connected through some network like we just discussed and how the inductive effect works. Okay. Summary here, strongest to the weakest. The greater the electron negativity on the same position relative to where the acid hydrogen is, creates a stronger acid because it stabilizes the complex after you pull off the hydrogen. And also the position. The closer it is to that, the stronger it is, the greater the inductive effect. That's another way to think about it. A couple different ways to think about it. Here, when you have the delocalization of the electrons, when you pull off the hydrogen versus the lack of delocalization or less resonance structures, you have a stronger acid. If you have the resonance structures or the greater delocalization, you have a weaker acid if you don't, because it's after you take the hydrogen off, it's either more or less stable. It's more stable when you have the resonance structures of the delocalization, and it's less stable when you don't. So therefore, it doesn't come off as easy, weaker acid. Same exact things I've been saying, just repeating it. More. Okay. Which member of each of the following pairs is stronger and why? NH3 and PH3. First thing I want to do is I want to see the N and the P, which one has a greater electron negativity. So which one is a stronger acid? It's kind of strange.
Right.
Yes.
It's easier to pull up.
Because of the size?
So where's P and where's N on there?
He's right below it.
P's below. So are we looking at at the hydrogen directly connected to the element it's connected to? Or is it connected to oxygen through a series of networks? Directly connected. Okay. So then how do we evaluate when something's directly connected? In terms of its acidity.
Oh, it's
Electron negativity and size. And size. Right? So then, in this case, what's a greater factor? The electron negativity or the size? The size. So which one's bigger, the N or the P?
The P.
The P. So therefore, the hydrogen's more easily going to come off the P than the N, and that makes it a stronger acid.
So size will play a bigger role when it's connected
When they're
directly?
connected directly.
Okay.
Size now does not play a role in the oxoacids, at least based on our lecture.
Okay.
Right? But it actually does, because it just means it's further away, meaning that the electron density between them has to go further apart. But we just said that I think the electron negativity plays the only role when it's connected to an oxygen, et cetera, et cetera. Okay. P is larger than N, causing a weaker bond and a stronger acid.
So only when it's directly connected
Yes.
is when size plays.
Matters. That, you know, maybe I should, let me do something here. Let me take you back to where that comes from. So here, trends among binary acids. Trends among binary acids, like this. Increase in electron negativity, increasing bond strength, right? Or decreasing bond strength, increasing bond strength. This way, okay? And you can see the ones that are lighter are the weaker acids, right? Harder to pull off the hydrogen. The ones that are more red are stronger acids, easier to pull, okay? So you see as you go down and you go across. This is binary. The very next slide, oxyacids. Here, you'll see we're only worried about the polarity that determines the strength of the acid. Even though the size doesn't play matter. So obviously it's bigger further apart, makes it harder for things to interact, but I'm not asking you about that part. I'm just simply saying that the polarity depends on two factors, the electron negativity of the Y, which is here, and the number of oxygens bound to it. So what doesn't play a role? Size. But it does, of course. It's just, it plays a smaller role in this context, so therefore we're just at this level saying it doesn't play any role. Okay. But it does, obviously. Does that help with that last question? Going back to these two slides here and making that distinction? Okay, so where am I at here? Okay, so the next one. HI and H2TE. So first thing I want to say is, where's I is over here, TE is there. Okay, so now they're about the same size, right?
But there's more hydrogen on there.
More hydrogen, but does the number of hydrogen matter? Would it matter if this was HTE minus?
Yes.
Yes, then it would matter, right? Because that would be what do we call those?
Or, catalysts.
Anion.
What do we call it when we have multiple hydrogen polyprotic? And as I progressively take off one hydrogen at a time, does it get more or less?
Right.
Okay,
Weaker, right?
it becomes weaker
Mhm.
because it's harder to pull that next one off because the electron. So, but having it complete here and complete here, it's a fair comparison, right? If I pulled one off and said HTE minus, or I could say it's conjugate, then it would be an unfair comparison. But since they're all there, so then the only thing I'm looking at, the TE and the I are next to each other, so are the size, which one's bigger out of curiosity?
TE. TE.
They're pretty close, but the TE is going to be a little bigger,
Yeah.
No.
Yeah.
Yeah, no, you're
right? Because of the,
The way it's
Down to the
going
left.
diagonal is actually going
Francine's
towards
Elias.
this part of it, right? He's going to the
electrons
left
in
to
the
right.
outer shell. As I increase the electrons in the outer shell, does it tighten it or
Tighten
make
it.
it
Tighten.
bigger? Tightens it,
Yeah.
right?
Times it. The more electrons, yeah, the tighter it is.
More electrons?
Yeah. The less of the
They're
sphere.
less, they're not pushing each other. If I go down a column, let me do this, 101. I go down a column,
Less electrons.
I get an bigger outer shell.
Right.
The atom gets bigger. Just atomic, we're not talking about molecules. Then if I go across, what plays the dominant role?
So going to the right is actually more electrons, less size. So smaller, going to the right.
You increase the electrons, but it doesn't get smaller, does it?
Oh,
Or
is
does
the-
it?
It does get smaller.
It does get smaller. Why? Effective nuclear charge.
Right.
Ah, right, the Chem 101. Go ahead, Efra.
So is it HI is
Well, I'm arguing that these are close to the same size. I was just reminding you that the actual TE is a little bit smaller than the I. but not enough to make a difference because it's not in a different shell. They're all in the same shell, but it's just slightly tighter.
My thing was that the difference couldn't also be that since I is more.
Well, that's what I was going to get at. Yes, you're 100% right. The I is more electron negative than the TE, and therefore, it's going to be the stronger or weaker acid? Stronger acid.
Right.
Because it's already got a greater separation in terms of the charge. So it's easier to pull it off. A larger electron negativity, stronger acid. Right?
So for the first one, we were talking about size, but this one, we were talking about electronegativity. It seems like.
Positioning. You got to look at the periodic table and see where they are relative to each other. Right? The TE is right next to the I, so there's no change in size. Very little, and that's what I was kind of emphasizing. There is a little bit of change, but not enough to matter here, so then the electron negativity plays a role. Over here, the electron negativity between the C and the S, kind of hard to tell, fairly close, not a big change in electron negativity between them, or the P and the N is really good. So the P and the N here,
There's more than that.
but the size is much different. There's a big difference in size. Yeah, what would be the electron negativity difference there? What would be the size difference? It's got a whole nother shell.
Yeah.
So the size is going to
So it's
overwhelm.
size first and then electronegativity.
Yeah, you could say that. That's fair. H2SO3, H2SeO3. So we go the S and the E. So what I'm trying to get you to do is make sure you go to the periodic table and say where are the differences in S and SE. So the SE is the same rationale as the first one, right? What if they had a different number of oxygens? Would that matter?
No. Oh,
Yes.
Yeah.
That would matter.
They have it.
But they have the same number of oxygens, so it's okay here. And by the way, does size matter here?
Yeah. That one has that.
Yes.
So I just got done describing that not too long ago, where I did say it does not matter in oxy. Remember, I went back to those two slides. I went all the way back to those two slides. And we looked at the difference between binary and oxy, and the oxy, the size, presumably, at least in the slides, does not matter. I said it does matter a little bit, but not to worry about it.
Right.
So then the electron negativity is the only thing that plays a role here. So SE and S, which one's more electron negative?
So
Which one's the right answer?
H2SO.
This one. Go back to those two slides that I just showed you. The binary acids, the size matters more, and the size and electron negativity both play a role in how the Y is directly connected to the hydrogens. In the oxy acids, the hydrogen's connected to the O. So the only thing that matters is the Y, which is connected to that O with the hydrogens, the electron negativity of the Y. Now, you can give rationale to how the size does play a role, but that role is too small or insignificant relative to the electron negativity of it.
So if you had H2S and H2SE, it would be the opposite? H2SE
Yes,
would be.
that's right.
Okay.
That's exactly right.
Okay.
So the question is, if I had just H2S and H2SE, which one is more acidic?
You go with the size, yeah.
Then you go with the size.
Okay.
Absolutely. And on the chart, it probably shows that, right? Didn't we see that red, the boxes with the reds? My guess is that you would see that this is going to be a darker red than this one. Anybody have those slides?
Yeah.
Instead of me going back and then twisting.
Yeah.
So which one is it? Yeah, so you can see here, the S and the SE, you see the SE is darker than the S. That means it's more acidic. But when it's connected to the oxygen, that doesn't play as great of a role. And in the slides, it claims it doesn't play any role. It does, but let's make it simple.
For the oxyacids, it says the hydrogen is always attached to an oxygen atom. In this case, it's attached to the sulfur or the.
No. These? No. The first part of your statement was true. The second part is wrong.
You said the more red it is, the more stronger?
Yeah. The stronger the acid,
Okay.
yes. Whenever you have, okay, so let's just look at this one, H2SO3, let's say, okay? This here, when the H's are in front, it implies it's an acid, which means it comes off. when you have the oxygens, this structure is presented like this, and you can do a Lewis structure of it. Now the hydrogens aren't sitting on the S. There could be some double bondage and stuff here, which we can figure out later. But the hydrogens are connected to the O's. These two are connected this way and this way, or this O, or whatever. So this representation, these are not connected to the S. If they were connected to the S, it would say SH2O3. The H's would be on the right side of the S. Because they're in the front, they're indicating that it's an acid already. And by having the oxygens there, they must be connected to the oxygen. Okay. If it, say, one was connected to the oxygen, you could say HSHO3. That means you would have one connected to the S. Okay. You very seldom would see a written SO3H2. Never see anything like that. No, these two are, that would imply that they're connected to the oxygen, but instead they just written in the front as the acid hydrogens. But then it's implied that those acid hydrogens are coming off the oxygen. Okay. Let's see, we're getting much, not even near as I thought, okay. Which member of each of the following pairs is a stronger acid and why? Same kind of questions. I'll let you, this is pretty quick. The 4 to 3, so the one with 4, that should be pretty obvious, and then greater number of oxygens. By the way, if it asks to explain, greater number of oxygens, that's all you have to put, right? No full sentences and back pages and all of that. I'm really just scanning as fast as possible, and by making something, this is, okay. Sometimes you want to make things more complicated. You don't ever, well, I shouldn't say that. Sometimes you want greater explanation for more complicated things, right? But when you could take something that's really complicated and simplify it so that everybody understands what you're saying, that is the best way to do it, right? And not just science, in anything, right? That makes you a good communicator. It means that you can communicate. If you can be the brightest person in the world and not be able to communicate what you know, who cares what you know? It's completely irrelevant to anybody other than yourself, which means it's irrelevant, right? But if you can communicate it, on recommendations of colleagues, when I've written recommendations for colleagues, one of the greatest things that I could write for that colleague is to say they can take difficult topics and simplify it, make it easy for everybody else to understand. Because when you can do that, that's when you fully understand what it is you're saying. And that's a hard thing to do, a lot harder than it sounds. So this is the start of that lesson is simplify it if possible. If you can't simplify it, you have to write a lot. That implies you're not 100% sure what it is. That's why you're writing so much. You're trying to find every possible way to explain in a way that you understand, hoping that I understand it. And the more you write, it's more likely the less I'm going to understand what it is you're saying, and the better chance you have of saying some things that are right and some things that are wrong. And if you say some things that are wrong, do I ignore those now? And just isolate the things that you say that are right and say, no, that means you don't fully understand it, which is the point. So make the answers, if possible, simplify them always as much as possible. And always try to think about the other, whenever you're writing something and putting something down, who's the reader? Who's the audience, right? Gear everything towards the audience, because if I'm talking to other scientists or I'm talking to a first-year chemistry, general chemistry class, I'm gonna say things differently, clearly, right? Yeah. If I say the same thing I say in here to, other scientists, colleagues, they're going to look at me like, what? Why are you telling us this? But if I go give a talk at Cold Spring Harbor, and then I kind of give the same information like this to you guys are going to say, huh? Look at the audience, and then write according to what they're expecting, right? And that's a good way to evaluate how well you really know the material, and how you can articulate it to somebody else so they understand it, because that's by far more important. If you, like I said, if you can figure something out but you can't articulate it to anybody, so what? Yeah. Right? But if you can explain it to everybody else, then you're doing a really good job and you understand it really well. Okay, here, this is pretty straightforward. We're doing the same kind of thing. So which one's more electron negative, Br or Se? Br. Okay. This is because there's no oxygen here. It's just more electron negative. So if I can go through these same, just keep doing the same stuff. Increasing order of acidic strength, so which one's what do I have? Br, Se, and then where's S? And then S, so it looks like Br, S, and then Se? Is that how it goes? Br, S, So this is going from order of increasing acid, so increasing acid strength. So that's based on size, of course, so this is the weakest, based on size, and then between these two, it's based on electron negativity. Right? You look confused? Jenna? S and S, so which one's the larger, which ones are the larger in size?
Oh, you're doing size for S and SE, okay.
Size, S and SE, SEVR, electron negativity.
Right.
Okay. Okay, here now we have the oxygens here, so this is going to be, we're increasing order of strength. That's the weakest, then that, then this. Okay. What did they do here? So this is the weakest.
Yeah.
But then they went this, then this. So in this case here, the CL and BR, where are they at? So in this case here, their CL is, they're claiming is a greater electron negativity.
Right.
And so they're saying that that makes it a stronger acid than this one, even though there are less oxygens.
And even though it's so much smaller.
Yeah, it's highly, that's ambiguous. I probably wouldn't give you that because you would have to know numbers, and
Yeah.
I haven't even shown you how to figure that out quantitatively. So
For that one,
if
you
you mix these two up, I really wouldn't care personally. If I gave you something that close, but it's not likely I will. Go ahead, Peter.
If the size is bigger, it's more acidic, right?
Yes, because it's easier. That's only for binary acids, not oxo acids again. Right? We keep recovering.
To the other one.
This one,
Yeah.
yeah, bigger, more acidic, increasing acid strength. This is stronger than that. SE is below S. Going down the column, you get bigger.
Right. Oxyacids would be
Right.
the electron negativity only.
Okay. Again. What is this one? Okay, which one's stronger here?
The one on the left.
This is the stronger acid because
Yeah.
this stabilizes it after the hydrogen comes off.
Right.
What about here? This is going to be stronger. A little bit of a twist. I put two of them on.
Right.
Use the same concept. This and this is the same. This is further away than this one. That one's going to be stronger and more stable. No big deal, right? I could easily throw in a third one. So
Did
what?
they miss the H in between the C?
Huh?
That
Oh,
just, it was
never
attached
mind.
to the.
Yeah, never mind.
Yeah. Oh, you just 1, 2, 3 C's. 1, 2, 3 C's.
No, I was looking at the H in between, but actually they put it in the H2,
Here?
and then
Yeah.
they put
There's
the
that H. They just
H3.
take that one off and they throw it. Right.
Yeah.
Okay. This for structurally, yeah, I forget that you're not as familiar looking at these, so that comes across weird. All they did was they take this H out here,
Uh-huh.
and they throw that the CL there where that H was,
And they put the H.
and this
on the
H
other
has to
one.
come over here to replace the
Right,
chlorine.
right, right.
Is that okay?
Cool.
Oh, so this is cool, right? Because what is this actually asking for? Something different. So here it's saying determine the stronger base.
Is that this?
So which is gonna make more hydroxide?
When I see that, what is the first thing I should be saying to myself? What's happening when I put each one of these in water,
Right.
right?
Yeah, you just pull it off.
So if I put them each in water, then I have this structure, well, let's just say structure 1, we'll call this R1, connected to the C connected to the O, negative. So this R1 now is, as I described before, is everything here, and we'll put the double bond C over here. So the R1 group is just everything to the left of this C here, this whole thing, okay,
Right.
for now. I mix this with water, and potentially
It's gonna
I
create
get
OH.
this thing pulls off a hydrogen, right?
Right.
And I'm left with OH minus.
So now
That's
you
why
have
it's a
the
base, just a perspective of what it is I'm talking about.
Right.
Okay, so now I say, okay, so is this thing more stable? This is where that other analogy and how I think about the weak or strong acids is better. If I take out the hydrogen, is this more stable or is this more stable?
That one. Wait, that one.
This one's more stable,
Yeah.
right?
Yeah, electron
So that
negativity.
means that this one is more willing to pull off the hydrogen, making it the. Now you see how thinking about it matters a lot. Because how else would you figure that out? Okay, does that make sense? Now it goes just like when you were thinking about the acids, when you pull them off from the inductive effect.
It's the opposite of it.
If I just look at so when I looked at the acidic structures like this, I said, what happens if I take the hydrogen off? I'm just saying, well, the hydrogen's already off here. That makes it easy to evaluate from a base perspective. Is this more stable than this? No. This is more stable, meaning that it's more comfortable sitting like this. Without the H, yes. Absolutely.
So which one is less stable, essentially?
The one that's less stable is the one more likely to pull off the hydrogen to make it more stable. That's exactly right. Yeah. Is that, see the way I describe it's huge, right? That changes everything in how to think about it, which should make it easier. Ephraim?
I was thinking it as if,
So like, but for a basic one, the reason for this one, it's this one, because the opposite of acids is acids.
we want to hold it stuff like that.
Got it.
It's opposite.
Yeah.
All I would say, you could, if you find a different way to think about it, that's fine. The way I think is the easiest way to think about it is which complex is more stable. That's the one that least wants to change. Therefore, it's the one that does not want to pick up a hydrogen more than the other one. How much more? Not asking you that. A stronger base because it does this. If it pulls off the hydrogen from the water, which is why I show you this, you create more of these. The more of these you get, the stronger the base.
Solution, right?
Yes, you got to think about it in multiple things. What is the base doing? And then which one is more or less stable by not doing that? Right?
They want to pull everything towards them. They want to be more stable.
Is that okay? Everybody get that?
Yeah.
You have to think, this is where you get tricked on an exam. Don't get tricked if you think about it the right way. Okay? What about this one? Which one's more stable? Let's do that. This is more stable, meaning this is the stronger base.
Right.
That's simple. When you break it down in a way that's easier to understand, right? Otherwise, you could sit there and play around. Well, which one? You go back and forth. If I add a hydrogen, what happens here? How does this work? This is essentially the inductive reasoning, right?
And if you know, it's the complete opposite of the
It's the opposite.
Right.
But that's why I described the acid that way also. Now you think of it the same way. Okay, so that covers everything for this chapter.
Have a good weekend.
Okay, listen up. Hold on.
It's only acid, but because it's more stable.
That seemed like a lot of information. A lot more than I thought. I didn't expect this to take a whole period. This should have taken, I thought, like, 10, 15 minutes. But that means there's some confusion, which is okay, because hopefully we're able to clarify some of that confusion, right? How comfortable are you guys with this material, the newer stuff? You need a little bit of time to think about it now?
Yeah.
Studying that on your own might not have been so easy without knowing the way I think about it, right? Then what do you guys think if we moved the exam to Tuesday and give you that extra time? It's already May, but I can give you that extra time to prepare for it. But that does mean, though, that I do need to move on. And we will get into the next chapter, buffers, I think it is, on Thursday. It will not be on the Tuesday exam, but it will be on the third exam. So it'll be just as relevant. So don't want people to not show up as a result of that. And because as you can see, for the same thing where I thought this was easy for you guys to cover, it wasn't so easy because it's not, it's how you think about it and put it into perspective, which is really difficult sometimes. Go ahead, Janet.
Will we be getting the electronegativity chart for the test?
If needed, but I don't think, have you ever needed to have any actual numbers? You just need to know the general direction, so no.
So we'll get
It'll be embedded in the problem. So, okay, so listen up. Okay, so I'm not going to start on the other chapter today. It's too late anyways, but
Some tips.
we are going to have the exam